This is the third lecture on calculus of variation. In the first lecture, we have developed the Euler-Lagrange equation from the variation principle, and in the second lecture, we have applied the Euler-Lagrange equation for the calculation of pure simple geodesics. We have calculated geodesic on a plane, which is a straight line, geodesic on the surface of a right circular on the curved surface of a cylinder, which is a circular helix, on the surface of a cone, which is a conical helix, and on the surface of a sphere, which is a great circle. Today we shall continue the application of Euler-Lagrange equation to few problems of historical importance. The first problem that we shall discuss is the Catenary problem, which is derived from a Latin word meaning chain. If we consider a chain and is allowed to suspend freely under the action of gravity, a chain of fixed length AB and is hung between 2 points then the shape of the chain that it takes for is called catenary. Here the principle is that the gravitational potential energy is a minimum. If we consider this is the x and y axis being the vertical axis, and y is equal to 0 level as the zero level of gravitational potential, then the potential energy V of the chain is governed by rho g yd as integrated from x1 to x2, where this is the limits, this is x1 to x2. We have considered a strip or arc length of ds, so it is at a height y, this height is y, and the mass of this part is rho ds, where rho is the linear density of mass density per unit length of the of the chain, and g is the acceleration due to gravity. We know the form of s and g. If we consider rho and g to be constant, then this becomes y1 plus y prime square to the power half dx integrated from x1 to x2. The shape of the chain is determined by the minimum value of v, and so we consider it as an extremization problem and call f in this case becomes y1 plus y prime square to the power half. F does not depend explicitly on the independent variable x, so we shall use the second form of Euler-Lagrange equation, which requires this derivative. Now the second form of the Euler-Lagrange equation is f minus y prime del f del y prime is equal to some constant c, which gives us this is for f, and for this part we have y prime square 1 plus y prime square to the power half is equal to c. On simplification we get c of y square is equal to c square 1 plus y prime square, or y prime is equal to dy dx y square minus c square by c square square root. We can write it as dx by c and This is dy y square minus c square. If we integrate this, this gives us x plus k from is equal to c times the integration, where integration is this, where I is defined as integration, where I is the integration dy y square minus c square. We substitute y is equal to c cos hyperbolic u, so that y square minus c square is equal to c square cos hyperbolic square u minus 1, which is c square sine hyperbolic square of u, and dy is equal to c sine hyperbolic u du. So the integration I becomes c sine hyperbolic u du, and in denominator we have c sine hyperbolic u. So this is du is equal to u, and u is equal to cos hyperbolic inverse y by c. So the equation becomes, so we have x plus k, when we use this, is equal to c times r is equal to c times cos hyperbolic inverse y by c. Thus, so, or y by c is equal to cos hyperbolic x plus k by c. This is the shape of the curve, which is known as the catenary. This shape of the curve seems to be similar to the roadway bridge, the girder connected with the roadway bridge, but this is not that. The girder of a roadway bridge assumes the form of a parabola, while the catenary is of this sort. One thing to know, that parabola is an algebraic equation, while this catenary is a transcendental equation. Another version of the catenary problem is called the catenoid problem. Another problem, catenoid. It is a catenary of revolution. The problem is like that. Let us consider two coordinate xy coordinate system, x and y coordinate system. We have 2 points, and we connect the 2 points by a curve of fixed length, and when we rotate this curve about the x-axis, where surface area is stressed out. Physically speaking, this surface area is generated when we take two circular rings, and dip them in a soap solution and pull them apart, such that the the, the two rings of different area, they have the they have their center line on a straight line which is perpendicular, or which are the axes of both the circles. If we pull this, then a soap plane is developed on this part, with two open circular ends, and this soap plane tends to attain a minimum area so as to minimize the energy due to surface tension. Here, the problem is to minimize the area. If we consider a strip line, a cylindrical section like this, then this part is y, and the circumference is 2 pi y multiplied by the arc length ds is the area, multiplied by ds is the area. So dA is equal to 2 pi y ds, and total area will be integrated over this. You note that the functional form F form is exactly same what we get in the case of catenary. So the catenoid problem most often is termed as the catenary problem in most of the textbook, but it is the catenoid. The surface area that is generated is a catenoid, and the curve is the catenary. Now we switch over to another very interesting problem, the Brachistochrone problem. The Brachistochrone problem means brachistos means minimum and chrone means time. So this problem is related to the minimum time. If we consider a particle subjected to a constant field, say gravitational field, then when it descends down from one point to another point, the path for which time is a minimum is the objective of the Brachistochrone problem. So the problem is minimum time problem. This is the problem related to the minimum time. We consider this is the horizontal axis and this is vertical axis, and we consider a particle descends down from a point A to point B, and at an intermediate point P. The coordinates of this is x1, y1, x2, y2, and that of is xy. So since it is moving under the action of gravity, and it has started from point A, started from rest at point A. So if we apply energy conservation principle at point A, then we have this is 0 plus mgy1, and if we apply this, it is half m ds dt square plus mg y1 minus y, or we get m cancels out all through, so ds dt is equal to twice g y under root. Let me check here. Or dt If we write the form of s, it is 1 plus root of 2g, then we have 1 plus y prime square. So we do the time taken when the particle descends from x is equal to x1 to x is equal to x2 is dt. This is equal to 1 upon 2g. So we consider f to be this is the for f for Brachistochrone problem. So it gives us that del f del y prime is equal to y prime divided by y into y prime square root. Since f does not depend on x, the second form of Euler-Lagrange equation, that is f minus y prime del f del y prime is equal to constant, gives us minus all we have this gives you c square y 1 plus y prime square is equal to 1. Or 1 plus y prime square is equal to 1 upon c square y square, or y prime which we write as a square minus y square by y. Sorry, I have made a mistake. This is c square y 1 plus y square. So this would be c square y, and this is, so we write it as a minus y by y square root. This is the form of the differential equation. We write it as dx is equal to y by a minus y dy. And if we integrate it, we get x plus k is equal to integration y a minus y dy. Now this calculation of integration, we put y is equal to a cos sine square theta. We use a sine square theta, so that dy is equal to twice a sine theta cos theta d theta, and quantity y a minus y dy becomes integration. For y it is a sine square theta. From this we have a 1 minus sine square theta, that is cos square theta, the entire thing within the square root, and we have twice a sine theta cos theta d theta. This cos theta cancels with this, and we have twice sine square theta d theta, which can be written as integration 1 minus cos of 2 theta d theta. On integration, this gives us theta minus half sine of 2 theta. There will be an a part, a will be there. If we take 2 out, so this is 2 theta minus sine of 2 theta, which we write b phi minus sine phi. And if we write this, this becomes b1 minus cos phi. So the path, the trajectory that is followed when the particle descends from A to B under the action of gravity, which is assumed to a gravitational force, to a force is assumed to be constant, then the shape of the curve is given by, this is the value of x. So this is the value of x plus k. If we choose the constant k to be 0, then we have x is equal to b phi minus sine phi, and y is equal to b 1 minus cos phi. This is known as cycloid. Cycloid is, if we consider a circle, of fixed radius, and if we put a point, this fixed point, and if we roll the circle along this, then the trajectory that this fixed point traces out is called a cycloid, and this is the parametric equation of a cycloid. So this is the Brachistochrone problem. Now reduces to the case that the minimum time taken for the particle to descend under gravity is along a cycloid. There is another related problem called the Tautochrone problem. Another problem is known as Tautochrone problem. I am not going to calculate the Tautochrone problem in detail, because the mathematics is a bit difficult. This is Tautochrone problem. The Greek word tatou means same, and chrone means time. So we consider a particle moving, starting from here, comes down to there, and it is found that the time taken, this is the maximum height, this is A and this is the minimum height B. The time taken in coming from A to B is the same when the particle comes from P to B. That is the time P to B time is same. So the same, what will be the shape of the curve when the particle takes the same time irrespective of same time to descend to its minimum position under the action of gravity irrespective of the starting point. So same time, this is time and this is same, so this is called the Tautochrone problem. Most popularly people solve this problem by taking cycloid as the trajectory and shows that the time this to this time is same as this to this time. I am not going to calculate this. This is only the statement. To end our discussion on the simple application of variational calculus, we consider the Fermat's principle. The Fermat's principle in geometrical optics, we know that it is as per Fermat's principle, the time taken by the ray of light when it passes from one point to another point is a minimum one. So this is the Fermat's principle. Least time. So if v be the velocity of a light ray in a medium, then the time taken t as the particle moves from one point to another point, t is given by dt from point x is equal to x1 to particle x is equal to x2. Now, d, we know that v is the velocity, then v is ds dt. So dt can be written as ds by v, and in geometrical optics we define refractive index as c by v, so that 1 by v can be written as n by c. So this becomes this quantity. Firstly, this is ds by v from point 1 to 2, and for v1 by v we write 1 upon c integration n, and for this part we write 1 plus y prime square to the power half dx integrated from x1 to x2. So our objective is to minimize t, so we define the function this f is equal to n1 plus y prime square to the power half, so giving del f del y prime is equal to n y prime 1 plus y prime square to the power half. And the second Euler-Lagrange equation, that is f y prime del f del y prime is equal to constant. Here we call the constant to be a, in order to avoid confusion with c we have already used, we get on simplification we get n by 1 plus y prime square to the power half is equal to a, or n is equal n square is equal to a square 1 plus y prime square. Now y prime is dy dx. So this is the, if we consider this is the ray traveling in one medium and other and moving to the other medium. So this angle is phi 1 in medium 1 and this is the angle phi 2. Then we have this is sorry, there is no square, so we get it as a square 6 square phi, or we get in cos phi is equal to a. This is a constant. If the ray propagates in a homogeneous medium, then n is fixed. So n is fixed, a is fixed. So we have cos phi is a constant. So the ray travels along a straight line. If the ray passes from one homogeneous medium to another homogeneous medium, then we have n1 cos phi 1 is equal to a is equal to n2 cos phi 2. This is for medium 1 and this is for medium 2. In geometrical optics, we generally use the angle of incidence theta 1, the angle of refraction theta 2. So we see that theta 1 plus phi 1 is pi. So we have theta 1 plus phi 1 is equal to pi by 2 is equal to theta 2 plus phi 2. So this equation simply becomes in terms of theta n1 sine theta 1 is equal to n2 sine theta 2, the Snell's law. In the next class, we shall apply the calculus of variation technique to the mechanics problem. That is, we shall switch over to the Lagrangian mechanics.